This is a quick video to clarify some of the points that came out from the discussion of problem 8.71, in which there's a piston cylinder arrangement which contains ammonia. So this is the piston cylinder arrangement. So it's containing ammonia. So the initial state is NH3 at 2000 kPa and 80 degrees Celsius. The initial volume is given as 0.1 meter cube. The piston is loaded with a linear spring. Okay, the ammonia is then cooled down to 20 degrees Celsius, at which point the quality is 10%. Find the work done, heat transfer, and the total entropy generation. Okay, so the application of the first law yields this. Okay, now what is W12 for a linearly loaded spring? It is equal to half of P1 plus P2 multiplied by mass times the specific volume difference. It is the area under the PV curve. Okay, so it is the area under this curve. Now, because both the states are known, if we apply, okay, so before first things first, so this equation will yield the work done. I already know the pressure and temperature at the first state, and also the total volume in the first state. I also know the second state as this. Using these properties, 2000 kilopascal and 80 degrees Celsius, I can then find out the specific volume. With the aid of the total volume and the specific volume, I should be able to find out the total mass. Okay, so the specific volume is volume of ammonia, T equal to T1, P equal to P1. Okay, so the mass is equal to volume by the specific volume. The volume is given as 0.1 meter cubed. So the mass is obtained as 1.317 kilogram. So the mass is obtained as 1.317 kilogram. So in order to find, so this is known. So in order to find the work done, we must know the pressure and the specific volume in the second state. So using these properties, and similarly the specific volume, okay, so everything is there. So the work done for a piston loaded with a linear spring is okay, this is the work done by the system. So work is done on the system because the ammonia is cooling down. Okay, that's obvious. Now we can move on to find the heat transfer, because we can know the internal energies using the states U1 and U2. So Q12 is equal to the mass multiplied by U2 minus U1 plus W12, where U1 and U2 have to be found out accordingly. So U1 is equal to int energy ammonia T equal to T1 and P equal to P1. and the U2 is equal to int energy of ammonia, T equal to T2 and X equal to X2. Using this we should be able to find out the total heat transferred. So the total heat transferred is minus 1485 kilojoule, which indicates that heat is lost by the system. Okay. So now we need to find the total entropy generation of the system. So S delta S for the system, because both the states are known, is simply equal to S2 minus S1. This is because once the two states are known, regardless of the process, reversible or irreversible, the entropy change is the same as S2 minus S1. Using the second law of thermodynamics, we can relate the S2 and S1 with the integral del Q by T over process 1 to 2 plus S gen from 1 to 2. However, in the absence of the knowledge of this process and what S gen is, because we directly know S2 and S1, the delta S for the system is simply S2 minus S1. But now we found out that the system is losing an amount of heat equal to this. So this is the heat gained by the surrounding. Okay, so delta S system is simply S2 minus S1. But if Q12 is the heat gained by a system, then minus Q12 is the heat lost by the surrounding. Therefore delta S surrounding is equal to minus Q12 by T reservoir. Okay, so the total delta S system plus delta S surrounding. Okay, make sure you understand the concept that if the two states are known, then regardless of how we went to the state, regardless of what the process is, ds system equal to mass multiplied by S2 minus S1, where we must write down the appropriate code and we must write down the appropriate point for the state 2. Okay, so what is DS system? So the system, because the system is losing heat, the system is going from a high entropy state to a low entropy state, but the corresponding increase in the entropy of the surrounding, the surrounding ds surrounding is equal to minus of Q12 by T ambient, where T ambient is given as, how much is it, 20 degrees Celsius. Just T ambient is equal to 20 plus 273.16. I don't write it directly as Kelvin because it's easier to debug if I make a mistake. Okay, so the total entropy change ds total is equal to ds system plus ds surroundings. The total entropy change is positive, so it means that this process is not violating any laws of thermodynamics. The loss in entropy of the system is made up by a greater gain in entropy of the surroundings. Okay, for the system and the surrounding, for this system, the absorbing amount of heat, because the temperature is not known, ds is equal to del Q by T plus ds gen. If you for the system, S2 minus S1 is equal to integral del q by t plus s delta s gen from 1 to 2. This is the change in entropy regardless of the state, regardless of the process. But the amount of energy transferred, if it is q12, then the surrounding has lost an amount equal to q12. So for the surrounding, delta S equal to minus q12 by t surrounding, t ambient. Okay. Now the key point is, for a control volume which encompasses the system and the surrounding, whatever heat transfer, it is only internal. It's only internal. This control volume or control mass is not receiving any external heat from the universe. This is the universe, in fact. This is by definition, this blue control volume is the universe. It consists both the system and the surrounding. So Q universe is 0. Whatever is there is internal. This is internal. So because Q universe is 0, we can write for the universe using this equation, ds universe is equal to 0 plus ds gen universe, because Q universe is 0. So this term will become 0. Therefore delta S universe is equal to delta S gen. If all the processes inside the universe are reversible, then delta S gen would be 0. Therefore the sum ds universe is equal to delta S system plus delta S surrounding, and we have already found out the two formulae. So this is for the surrounding, this is for the system. Okay, this is how you do the problem. So it was not necessary to assume that the process is reversible to get rid of this. In fact, if we were somehow able to measure what S gen is, what this integral is, because see, during this process the temperature is actually varying, the amount of heat transfer is something and the temperature is varying, this integral would be rather difficult to evaluate. But S gen is also difficult to evaluate or measure. So the effect of these two terms has been given as the two states, state 1 and state 2. States 1 and 2 have already inbuilt the effect of this integral del q by 2 and S gen, and thus the change in entropy as it goes from state 1 to state 2 is simply S2 minus S1. We don't have to evaluate in these integrals. And correspondingly the change of entropy of the surrounding is minus q12 by t ambient. I think we have done similar problems to this. So I'm keeping this inside. Okay, what was the problem number? The problem number is 8.71. Okay, so I hope this solves the confusion that we had.